morning session, and the first lecture is by Professor Rubakov about cosmology.
Okay, good morning everybody. Yesterday I claimed that we know several important facts about cosmological perturbations, density perturbations in the first place, and also we have limits on gravitational waves. And the question is, how do we know all that? And key player here is cosmic microwave background. You all, of course, have seen, presumably, this nice picture, which is a photographic picture of our universe when it was 370,000 years old, and temperature at that time was 3,000 degrees Kelvin. That corresponds to redshift of 1090. So it was pretty young at that time. One thing to notice about this picture is that, of course, it's not the picture of temperature. This is temperature, color-coded, and of course, this is not the temperature map, because, of course, the temperature itself is a lot higher than temperature fluctuations, one thing. And another is that it is cleaned map, because there are a lot of foregrounds. Cosmologists use this word instead of backgrounds. Foregrounds meaning that there are a number of sources of different kind that emit photons, so that one has to clean the map. In particular, there is huge emission from galaxy, our galaxy, and also there are point sources like stars or other sources. So one has to clean. And after cleaning, which is by itself rather complicated procedure, you get this kind of picture and try to analyze it. So temporarily, our universe was not homogeneous, completely homogeneous at that time, and there were colder places, there were hotter places, but take a notice that overall scale here is hundreds microkelvin, a few hundred microkelvin. So compared to the temperature, it's just what I claimed, that the fluctuations were at the level of a few times 10 to the minus 4. It was very homogeneous, but there were little fluctuations here and there. And just by looking at this picture, you see that there is no pattern here. Essentially, it's kind of a random pattern. So it's conceivable that we are dealing with a random field. How does one make sense of this sky map? Convenient way to get information from it is to decompose this delta t of n. N is the direction on the celestial sphere. One decomposes into spherical harmonics. A, L, M, sum over L and M, A, L, M, Y, L, M of N, and extracts coefficients A, L, M. These are measurable quantities. One measures them, and these are presumably random variables. Looking at this picture, one understands that these are kind of random variables. Now, if my field is isotropic random field, then my fluctuations delta t of n, delta t of n prime, the correlation function of these fluctuations over the sphere is going to be a function of the difference. So if it's a homogeneous and isotropic field, isotropic random field, then there is no preferred direction in the first place, and also there is everything depends on the difference of these two ends, and this translates into essentially momentum conservation, namely the correlation function of this ALM, L prime and prime, is a the delta symbol, CL times the delta L prime, delta M prime. There is no dependence on M because of, again, rotational invariance of the correlation function. So these CLs are the coefficients which characterize for you the distribution of temperature on the celestial field. Now, one word is that what is averaging here? When we are talking about random fields, we are talking about ensembles. In each member of this ensemble, the random field takes a definite value. Of course, there is a very definite value for the temperature at a given direction in space. So we're dealing with one single realization of this field. You have just one universe. So we are talking about a single realization of a random field. And because of that, you have just one measurement, essentially. So averaging here, theoretically, is averaging over the ensemble of the universes, like ours. But we are dealing with one single realization of the field. And therefore, whatever the predictions you give for these CLs, they will not be precisely matched with the data, because you have uncertainty, you have statistical uncertainty. If you measure these CLs as a sum, 1 over 2L plus 1, or 2L plus 1 of these CLs, M runs from minus L to plus L. So you can measure these CLs as ALM modulo square sum over M. Should discard the complex things. You measure these CLs in this fashion. You have 2L plus 1 measurements of these CLs. You average over 2L plus 1 measurements. Therefore, you have statistical uncertainty. And this statistical uncertainty is large at small values, value of L. For large L, it's tiny, but for small values of L, you have considerable uncertainty, which is called cosmic variance. So now, these CLs are called temperature anisotropy spectrum, and that's precisely what people measure and plot. And in fact, in this area, the progress is very fast. That's how the temperature anisotropy spectrum looked, say, 6 years ago. There was also already WMAP data. These are the WMAP data. And then there was a mess in the high L tail. So this is L here, and here, well, okay, this is essentially the CL. Okay, the certain normalization. The progress is very fast, and today the picture is a lot more detailed. Again, here is WMAP data, and here are the data from ground-based measurements of relatively small patches of sky, from which, but with much better resolution, from which one can infer the CLs. Here is actually CL times L plus 1. That's the convenient way to present the data. So you can infer the tail of high multiple moments. Multiple moments, of course, are related to angular scale, because the essentially expansion of spherical harmonics is the same thing as the Fourier expansion. Large L corresponds to high momentum, and correspondingly small angle. So we are talking about angular scales starting from essentially 90 degrees to very small angular scales below a degree. Okay? Now, with Planck, which has flight, and we are awaiting for the data from Planck, this picture will be cleaner, especially in this region of large multiple moments, okay, large L. There, this curve will be given with much better precision. On the other hand, this part, if WMAP didn't do any mistake, this part is not going to change. All these error bars actually refer to cosmic variance. It's not statistical errors on the measurement itself, it's rather cosmic variance. And it's huge in here, right? For example, probably it's more visible. In this plot, you have quadrupole, the L equal to 1, which is quite low, right? Now, question, is it a physical feature of the cosmic microwave background, or is it statistical fluctuation due to single realization of our universe? It's not clear, and we may never be able to figure that out. Might be a statistical fluctuation. Although there is a lot of noise, theoretical work, trying to explain this feature. Okay. So now, I told you that we have a very simple primordial spectrum. However, we have a pretty complicated pattern of temperature anisotropy spectrum inferred from cosmic microwave background. What's happening? What's the reason between this, apparent discrepancy? The reason is simple. The reason is evolution. Perturbations stay constant with flat power spectrum, or nearly flat power spectrum, only when they are superhorizon, only at very early times. Once a given mode has the momentum higher than the Hubble parameter, it starts to develop. The evolution starts to play a role. So what do perturbations do after they re-enter the horizon at the hot radiation-dominated or matter-dominated, very long wavelength perturbations enter the horizon at matter-dominated epoch? What do they do then? Well, we have perturbations of dark matter. Dark matter perturbations just stay there. This is pressureless fluid. This is just like dust. So if you have overdensity somewhere in this dust, then it stays at the same place. And the only evolution is due to gravitational instability, which means that if you have some overdensity in here, it produces a gravitational field, and this gravitational field attracts more material to this place, so there will be more and more overdensity in this particular place. Right? That's how the gravitational instability works, or Jeans instability works, and that's why these tiny fluctuations at the level of 10 to the minus 4 become large, become a full 1, and then galaxies form. That happened later, much later after the recombination epoch, but it works to some extent also before recombination. So dark matter perturbations stay constant, stay at one and the same place, and increase in amplitude. Right. Now, before recombination, there was another component in the cosmic medium, which is photons and baryons, tightly coupled. This is one and the same fluid because baryons interact with photons and the electrons there. And this baryon photon component is not pressureless. It has velocity of sound approximately equal to 1 over square root of 3. That's essentially a relativistic component because photons dominate in this component. Baryon density is relatively small compared to the photon energy density in this component before recombination. So we are dealing with a fluid with pressure, and in this fluid, if you have overdensity here, it starts to make a sound wave. So we have sound waves here. Okay. Now, these baryon photon delta rho over rho stay constant in amplitude and oscillate. So there is a prefactor that depends on the initial conditions, right? We are talking about linear regime, so everything is proportional to the initial conditions. And then also they oscillate with a well-defined phase, cosine, from 0 to t of the momentum times velocity of sound, dt over a. Okay. That's our formula. That's physical momentum k over a. K times sound velocity over a is the frequency, so that's the oscillating part, the oscillating term. Now, in principle, there are also tensor perturbations or gravitational waves. They also oscillate, again with a well-defined phase, but their amplitude after horizon crossing, after horizon entry, decreases like 1 over a. And that's normal redshift. We remember that the amplitude we calculated yesterday for any field goes like physical momentum. Say we discussed scalar field, and the same happens for gravitational waves. The amplitude goes like physical momentum, and physical momentum redshifts like 1 over a. So this is essentially redshift. That does work for density perturbations because we normalize density contrast to the average density, and therefore this quantity stays constant in amplitude. All right, so why is it that the phase here is fixed? The reason is that our perturbations were superhorizon, as we think, and therefore the initial condition was fixed. The perturbation was constant, time independent, when the perturbation was superhorizon, very early times. The amplitude was non-zero, and the velocity, the derivative of this rho, delta rho, was 0. And that's precisely what happens here. At time equal to 0, you get finite amplitude and 0 time derivative. So this phase is fixed by assumption, essentially, for the time being, that our perturbations were superhorizon. Okay? Now, all these perturbations produce perturbations in temperature, and perturbations in temperature, delta T over T, get several contributions. One contribution comes from the fact that you have different density of baryon photon component at different places in space, and therefore you have different temperature. The energy density is proportional to temperature to the fourth of photons. So it's basically, the first term is basically a quarter of delta rho over rho of the photon component, or baryon photon component, right? This is just the fact that the photon energy density is proportional to temperature, temperature to the fourth power. Stefan Boltzmann law. The second part has to do with the fact that you have gravitational potentials. And remember, probably some of you know, that Newtonian potential phi, which is just the usual Newtonian gravitational potential, it is equal to a half of h naught naught. The derivation in the 0, 0 component of metric. So you have Newtonian potentials in your universe, and if a photon climbs out from the potential well, it loses energy, and conversely, if your potential has a bump, then it rolls down from this bump and gains energy. So the fluctuation we see is also proportional to the Newtonian potential. And there are two terms in the Newtonian potential. One is due to perturbations in baryon photon component, and another is due to perturbation in dark matter. Right? Both density contrasts in baryon photon and dark matter, they both produce gravitational potentials. Okay? Now, there is one more term, which is Doppler term, right? If your baryon photon component moves from you towards you, then you get a Doppler effect, right? And this motion, if you have, you know, the sound waves, then of course there is motion, right? So there is this Doppler effect, which is proportional to the direction of your view times velocity, probably with minus. And is the direction on the celestial sphere, then there is this term. Finally, there is one more term, which has to do with the fact that photon that travels to us from the recombination epoch goes through gravitational field, right? There is still gravitational field on the way of this photon towards us, and that produces what's called integrated Sachs-Wolfe effect. Okay, and this is equal to integral along the photon path from recombination epoch to our present epoch of gravitational field. And it turns out that this is h naught naught dot minus hij dot and I and j integrated over time. This is again in the gauge g naught I equation. Dot is the time derivative. So, and it's clear that if the metric doesn't change in time, then the photon comes in, say, goes down the potential well, climbs out from the potential well, and nothing happens to it in the end. So the effect is proportional to the time derivative of metric coefficients along the photon path. Okay? So that's a very simple formula that determines for you how perturbations in all these components, dark matter, baryons, gravitational waves, if any, how it shows up in the temperature and isotropy we see. Okay. So gravitational waves, by the way, play a role in here only, because these are Newtonian potentials. These are not transverse traceless part of the metric. Everything else refers to the photon, baryon photon component and dark matter. But this term involves also gravity waves. Okay. Now, clearly, you now understand the pattern, basically, this oscillating pattern, because you have different terms. So let me show you one picture. So that's how the perturbations in different components behave at different epochs. So we're talking about a single fixed momentum k, or wave vector of a perturbation, for baryons and photons, the amplitude stays constant until recombination. They oscillate together. The oscillating part is not shown, but they oscillate. Dark matter part grows after equality between matter and radiation due to gravitational instability. It slightly grows even before. There are kind of transition periods where the evolution is more complicated. And after recombination, which is not captured by essentially by the cosmic microwave background measurements, what happens is that there are potential wells due to the dark matter. Delta is delta rho well. Dark matter perturbations, they produce gravitational wells, and baryons fall into these gravitational wells, and in the end, perturbations in baryons, which are now decoupled from photons, perturbations in baryons and dark matter work together. All right, now you understand why there is this complicated pattern with oscillations in the cosmic microwave background spectrum. That's because if we are talking about given L, we are talking essentially about the Fourier component of the temperature on the sphere of last scattering, sphere of recombination. At the time of recombination, you have you see a certain part of the universe, which is essentially two-dimensional, right? Because you're dealing with essentially fixed value of time. So you look at a certain sphere of last scattering, and this Fourier expansion over harmonics on this sphere is basically Fourier expansion in momenta on this surface, on this last scattering surface. So if you have three-dimensional momentum k, then basically you're dealing with L proportional to this k. Of course, it's not exact because this is three-dimensional momentum, so the directionality may not be normal to our line of sight. This will be exact for perturbations that are normal to our line of sight. For others, there is a little more complicated relationship, but basically, if you look at a given value of L, you measure perturbations as they are at the recombination epoch with momenta of order of L. Okay? Times the distance to the, so L is essentially K times the distance to recombination, to last scattering. Okay? Coordinate distance to the last scattering surface.
Sorry, but what about M?
M, for given, M is a directionality, right? If you look at the surface of last scattering, then there is the overall scale of the perturbation, and also there is directionality. And M captures directionality. Okay? So that's why nothing on average should depend on M. Okay, this ALM on average should not depend on M. Yes?
Can you just explain why this plot is periodic?
Sorry?
Why is this plot periodic?
I'm just going to do that. Now, where do the oscillations come from? They come from the fact that all these terms related to baryon photon component, all these terms oscillate in time, but we are interested in these terms at the recombination epoch. So, as recombination epoch, this is just this integral, right? Now you understand that this integral is now oscillating function of k, right? And since it is an oscillating function of k, then these contributions are oscillating functions of k. And according to this correspondence, the things we see, the temperature anisotropy we see, is an oscillating function of L, right? In other words, some perturbations, for some perturbations this cosine is 1, right? This happens when the momentum is just right, or -1, since we are talking about modulus. For some perturbations this cosine is large, and this gives you large contributions due to this delta rho over rho and the potential phi. By the way, this Doppler term is relatively small, so it doesn't play a profound role in the temperature spectrum. More important are these delta rho over rho and phi terms, the gravitational potential terms. These oscillate, and these are the biggest when this momentum is just right, when this cosine is 1. And that corresponds to a certain value of L. Okay? So all these peaks here correspond precisely to those momenta for which this cosine is 1. Okay? And clearly this is oscillating pattern, periodic. But one thing to notice is that it doesn't oscillate to 0. Cosine oscillates to 0. And the reason is this dark matter term, which doesn't oscillate, which is a smooth function of momentum. And all this, non-oscillating part, the average part here, is due to dark matter. Okay, so there is a coherent superposition of the baryon photon contribution, dark matter contribution. This coherent superposition, and that's non-trivial, assuming that the initial condition for dark matter and baryon photon component is one and the same. Okay? That both of them is proportional to one and the same random field. That's a non-trivial thing. I will talk about that a little later. Okay, so we now understand this oscillating pattern. Now you may ask what happens at high L's, why the perturbation spectrum goes down essentially exponentially, right? This is log scale here. It goes down essentially exponentially, and the reason is that the photon mean free path at recombination epoch, a little bit before a recombination epoch, is finite. Okay, so photons actually diffuse out of over-density regions and smear out the perturbations. Okay, smear out the perturbations in the photon component get smeared out. That's called silk damping. So you do expect that at short wavelengths there will be very little perturbation because photons stream there and dilute any perturbation that we had originally. So that's also pretty well understood, this feature. Now if we look at this power spectrum, then we see several things. And that's another little bit outdated version of this semiannual spectrum. By the way, notice that in many of these plots, the scales, the horizontal scales, are rather weird. You have logarithmic scales at low multiples, and then linear scale at high multiples. So that's not what we usually do when we plot our results, but that's done for convenience of representation. Here, similarly, you have logarithmic scale here at small multiples and linear scale at high multiples. So that's kind of a standard thing to do when plotting the CMB anisotropy. Anyway, that's another representation for it, another way of presenting it. A little bit outdated data, but again, this is WMAP, and these are these black dots are ground-based experiments. Now, what we see here is that we have nearly flat part at low multiples. Now, at low multiples correspond to small momenta, right? And if we are talking about multiples below, say, 30 or 40, then we are dealing with modes which are still superhorizon at recombination. They had no time to develop. The momentum is so small, the frequency is so low that they haven't developed even until recombination. Okay? And as we discussed, the spectrum is flat, and that's essentially the picture here. The spectrum is nearly flat. Now, all these peaks are due to these oscillations that I told you. In fact, one can even see an interesting feature. An interesting feature is that, you know, the lower the multiples, the higher the peaks. The first peak is the highest, second peak is second highest. Third peak should have been even lower, but it isn't. And the reason is the constructive interference between the baryon photon contribution and dark matter contribution. So the odd peaks tend to be a little higher than even peak on relative in relative terms. Okay. So now the point is that the very existence of these oscillations is actually proof that the perturbations were superhorizon. I told you that we know that perturbations were superhorizon, and that's the proof that there are oscillations. If the perturbations were created in the universe by some mechanism at the hot epoch in a causal way, when they become subhorizon, when they become short wavelength compared to the Hubble length, then one would not expect that this phase is fixed, is very well defined, right? Because if that was so, then you would expect, again, oscillations, but from some creation epoch at hot stage, after horizon crossing, and this creation epoch would be at least Hubble time, Hubble period, and that would mean that this cosine has rather arbitrary phase. There would not be a very definite phase under this cosine, and therefore all this nice structure with peaks would not be there. So the very fact that there are oscillations in temperature power spectrum is the proof that the perturbations were superhorizon. So when we talk about inflation or anything like it, or substituting inflation, we are not joking. There is direct evidence that there was a phase, there was a stage before the hot epoch. Indeed, if you start doing physics and try to really create perturbations at the hot epoch, you can do that. And people have played this game for some time before these peaks were observed. For example, you can have lumps of matter, say cosmic strings or textures, something like that, some topological defects, which would attract material and produce perturbations for you. And these fail badly in predicting the temperature power spectrum, because these predictions are like here. There are no peak structure, just smooth curves, and this is badly wrong. So that's an example that we actually know what was going on, that the perturbations were superhorizon rather than created at the hot epoch.
I'm sorry.
Yes?
If we had balanced universe picture,
Yes?
we have similar oscillations.
Yes. Yes. Yeah. The oscillations have to do with the fact that the perturbations were built in before the hot dipole. That's all. That they were superhorizon before the hot dipole. How you produce them, whether you have inflation or bouncing universe with its own mechanism, doesn't matter. Okay. Right. Now, if we had tensor perturbations, then they would contribute also to this temperature fluctuation. And as I told you, short wavelength tensor perturbations are actually damped by a factor 1 over A. After they exit the horizon, they become smaller amplitude. Their amplitude decreases. Therefore, the largest contribution is at low momenta from gravity waves, at low momenta. So you expect a contribution to the temperature anisotropy large at low momenta and decreasing rather fast at higher L. Okay, and the limits that I showed you was trying to, dig out if there is any enhancement of your spectrum of temperature spectrum at low moment. And since it doesn't seem to be so, we get bounds on the admixture of tensor modes. Now, before going further, let me note that the CMB temperature anisotropy and also polarization is sensitive to various cosmological parameters. So, for example, the curvature, three-dimensional curvature, would shift the position of the peak, right? Because we know that if we had a given absolute length, then this interval of this length is seen at larger angle on a sphere as compared to plane, right? So the peaks would be shifted, the angles at which you see the most pronounced perturbation would be different, would be shifted, and that's shown on the left figure. Similarly, if you have dark energy density, then the distance to the last scattering surface is different, and therefore, again, the peaks get shifted. There are a number of other effects. For example, one thing which is important is that I was assuming that perturbations were adiabatic. What does it mean? Adiabatic means that you have primordial perturbations are adiabatic, which means that you have perturbation in energy density, total energy density of everything. Photons, dark matter, everything, but the chemical composition is the same everywhere. Chemical composition is characterized by the number density of, say, dark matter particles to entropy density, right? Both scale like inverse cube of volume, right? So this ratio could in principle be different in different places in the universe. For adiabatic perturbations, it's 0. So perturbations in everything are at one and the same place. In dark matter, photons, neutrinos, baryons, they're all in one and the same place. Okay? These are called adiabatic perturbations. Of course, you can in principle think that there might be other types of perturbations, a different one with 0 energy density perturbation, but perturbation in chemical composition, say dark matter density, could be different in different places in the universe. That's called entropy perturbations or isocurvature perturbations. Isocurvature because there is no perturbation in energy density and hence no perturbation in gravitational potentials. So these entropy or isocurvature perturbations could be there, and they will produce completely different pattern of CLs, of temperature anisotropy. Okay? That's how it would look like. And since we know that the picture is like here, we know that entropy perturbation is not there. And that's quite natural, because if we think that, say, dark matter was produced at the early epoch, then before the production of dark matter, before the generation of dark matter in the early epoch, you had one and the same fluid. So if you have one and the same physics everywhere in space, then you expect equal amount of dark matter produced in different places in space, which means that the chemical composition is one and the same everywhere. So adiabatic perturbations are very natural if we observe an admixture of entropy perturbations. That would be a revolution. That would mean that our thoughts about the generation of dark matter are completely wrong. That dark matter was generated at inflationary epoch or some maybe reheating epoch at some very early stage. So that its perturbations are unrelated to perturbations in baryons and photons. Until now, there are only limits, and the limit on a mixture of dark matter perturbations, entropy perturbations, is at the level of 5% or so. Now, okay, what else do we know? We know that, now, by the way, I told you that curvature of space is negligible today, and that comes from the fact that the picture of delta G over T is very sensitive to spatial curvature. Today, the limit on spatial curvature is better than 5%. So omega curvature from this data, curvature omega is less than 4.6%. So our space is Euclidean to very good precision. We know that experimentally. Okay, there are dependencies on everything. In particular, baryons, the admixture of baryons, the baryon number density in the universe plays an important role here. And it's clear that, I mean, and this illustrates this, that once you have for universes with different baryon content, you would get completely different pictures also for cosmic microwave background. The heights of the peaks are very sensitive to the baryonic omega, the contribution of baryons to total energy density. So from CMB alone, you get a very good measure of baryon number density and baryon fraction. Okay? So, you know, you're very sensitive to cosmological parameters, and combining this CMB data with other data, which I was talking about at the first lecture, you get very precise determination. All right. Now, beyond the standard model. So, let me remind you that our standard cosmological model involves several ingredients: cold dark matter, time-independent dark energy, scalar adiabatic Gaussian perturbations with power spectrum. Very simple picture. Now, we can question all these properties. We can question whether dark matter is cold. One can think of warm dark matter. Warm meaning that cold means that the velocities of dark matter particles are never relevant. They are so slow that velocities never play any role. Warm dark matter means that at early epoch, the particles were relativistic, they had high velocities, they streamed out of overdense regions, and then, therefore, they smooth out short wavelength perturbations. Okay? When their momentum gets shifted down to its mass, they kind of slow down and eventually freeze into cosmic frame. But in the beginning, they dilute short wavelength perturbations. The effects are less structure at small scales. Dwarf galaxies will be less abundant. And that's nice, because there is a apparent problem with the prediction of cold dark matter, namely that the dwarf galaxies tend to be overproduced as compared to observations in the cold dark matter scenario. So warm dark matter may be good from this respect. And also there are problems with two strong kind of singularities in the centers of galaxies, cusps, again predicted by cold dark matter. Warm dark matter may be useful in this respect as well. But there is another problem that you want to have small structures formed early to produce reionization for stars must be formed pretty early. And warm dark matter has difficulty with that. So whether dark matter is cold or warm, from the viewpoint of cosmology, is not clear. Cold dark matter looks fine, has its own problems, but maybe these are problems with observations and numerical simulations of structure formation rather than the problems of cold dark matter itself. So it's a matter of some debate, although most people think that cold dark matter works well. Now, time-independent dark energy. That's a very important question. Why? Because if you have cosmological constant or vacuum energy density, then the energy momentum tensor must be proportional to metric, right? In locally Lorentz frame, it must be just a constant times 1 minus 1 minus 1 minus 1. Okay? Just a cosmological constant. And this you can, in general, write your energy momentum tensor in locally Lorentz frame as density in here and pressure in here. So for cosmological constant, energy density is constant in time. In other words, pressure equals to minus energy density. If this is not so, then our dark energy is not a constant, it's not a fundamental constant of nature, it's rather a field. It's rather a contribution of some field that varies in time. One parameterizes the possible dependence of dark matter, dark energy density on time in the following fashion. One writes 1 plus z times 3, 1 plus w. Here is this w determines for you whether dark matter is constant in time or not. If this w is minus 1, then there is no dependence on time and hence on the redshift. And furthermore, one can think of w as a function of time itself. And one parameterizes this like w naught plus w a z over 1 plus z. That's just one parameterization, one possible parameterization of the dependence of the dark energy density on time or on redshift. And using all this cosmological data I was talking about in these lectures, one can figure out whether these w's are, w is minus 1, whether this WA is 0 or not. Okay, here is the plot. You see W0 equal to 1 and WA equal to 0 are consistent with observations. Okay, these are 1 and 2 sigma contours. So for now, dark energy is constant in time. And that's a pretty dull situation. If this is just a constant of nature, it's just a constant of nature. Nothing interesting. Very weird. 5 GeV or 4 GeV per cubic meter. What is this constant of nature? Very, very strange. But we don't have any you know, clue on the origin of this parameter, it's just a parameter. Much more interesting would be the situation if either W, if you're somewhere away from this point where W8 is 0 and W0 is -1. If we are somewhere here, then the situation is a lot more interesting. Then there is dynamics behind the dark energy, there are fields, ultralight fields or something like that. Maybe gravity is different from Einstein gravity, also a possibility, but that will be very interesting. For the time being, the cosmological constant is a big guess.
What is the precision here?
Huh?
What is the precision?
Precision, well, that's W0. -1 is here. This point is -1.2, 1.3. So the precision is not very high.
Does Planck
Well, I don't expect that you're going to be much better with Planck. Slightly better, but not dramatically. Okay. Now, that's for homogeneous part of our standard model. And of course, inhomogeneous part is also very interesting. Indeed, perturbations, as we saw, is a window to the pre-hot epoch. And presently, we know only very basic things about perturbations. These are adiabatic perturbations, which are Gaussian, and slightly tilted, probably, power spectrum. Now, gravitational waves. Discovering gravitational waves will be proof of inflation. No other scenario predict sizable gravitational waves at large wavelengths. So, detecting gravitational waves by using cosmic microwave background will be a discovery of inflation. That will be a triumph of inflation. As I told you yesterday, that's the current situation. The tensor to scalar ratio is only bounded. There is no signal. I don't expect much from Planck in this regard, because what we first of all, what the tensor perturbations do is to introduce some more power at long wavelengths, but these long wavelengths have been measured by WMAP already within the precision of cosmic variance. So I don't expect Planck to do much better job. Maybe this, this limit here will be somewhere down there. What is interesting is that gravitational waves produce a certain kind of polarization. Polarization in cosmic microwave background has been already observed. This is polarization map with not very high precision by WMAP and other experiments. But this pattern of polarization is correlated with temperature. Just the fact that photons coming from hotter places scatter off the last time, and the Compton scattering actually produces polarized photons. So there is a correlation between polarization and temperature. So, and that's not particularly interesting. That's what you expect from adiabatic scalar perturbations. What gravity waves will do, they will produce another type of polarization. Here it is, the B mode so-called. Okay? And that's a different pattern of polarization, which is unrelated essentially to the temperature anisotropy. This has not been observed, and hopefully there will be dedicated polarization experiments measuring polarization of cosmic microwave background with very high precision, and they are the best candidates for discovering gravity waves. Now, coming back to adiabatic perturbations, to the scalar perturbations, we parameterized them in primordial perturbations in a very simple way, like here, with constant spectral index ms. Okay? In principle, this simple form may not be there, in particular this ns, the scalar spectral index, can run, can depend on the momentum itself. Now the question is, does it run really? In simple inflationary models it doesn't. Its running is essentially negligible, it's very little. So again, if you see running, then you get interesting hints towards the very people of the universe. Are there a mixture of entropy modes? I was talking about that, yeah. And if there is a mixture of entropy modes, the life will be very interesting. We will have to rethink of our understanding or expectation for the dark matter generation, for baryon symmetry generation. There are other two things which are, again, very important. These are non-Gaussianity. This is very hot topic. Meaning, for example, that a 3-point function of your perturbation doesn't vanish. Now you understand that if you have 3-point function, it's even if you have homogeneity and isotropy on average, this is a function of many variables, like x minus 1 modulus, x minus z modulus, various scalar products, etc. So if we see non-trivial 3-point function, then we'll have entire function, new function, that will characterize our perturbations. And different models predict different types of non-Gaussianity, different shapes of this function. Again, simple models of inflation predict very small non-Gaussianity. Discovering non-Gaussianity will mean that simple inflationary models don't work. Finally, statistical anisotropy. In terms of 2-point function, this means that the power spectrum depends on direction of 3-dimensional momentum. Okay? And that means that originally the universe was not isotropic. There was some directions that were preferred in the very early universe, before the hot Big Bang. Again, that's essentially inconceivable in simple inflationary models. And in other models, you do get statistical anisotropy. An interesting thing is that WMAP does see statistical anisotropy. For WMAP, there is, of course, a constant term independent of the directionality, but there is also a term like this, Wij, Ki, Kj, K squared, with some constant tensor Wij. Okay. And the WMAP is non-zero. However, its axis is normal to the ecliptic plane. Ecliptic plane is the plane of rotation of our Earth around the Sun. And once you have an anisotropy normal to this ecliptic plane, then you think that it's going to be a systematic. It's not real, it's not in the cosmic microwave background, it's systematics. And people discuss various origins of these systematics. So Planck will be able to settle this issue, and actually it will measure or put much stronger limits than currently on non-Gaussianity and statistical anisotropy. That's real strength of Planck, because it will measure long tail in L. It will have a lot more short wavelength data, and therefore a lot more statistics, because the more data you have, the more statistics you have. So non-Gaussianity and statistical anisotropy, that's what possibly be observed by Planck. We'll see whether this works or not. So there are many questions beyond the standard cosmological model. For the time being, standard cosmological model works surprisingly well. So let me finish my lectures by asking these questions. Are we going to be stuck with standard cosmological model, like we are stuck with the standard model of particle physics. It may very well be that standard model of particle physics is the end of the story. Likewise, it may very well be that the standard cosmological model is the end of the story. Hopefully not in both cases, but nothing is guaranteed. So presently we're in a very interesting situation, both in particle physics and in cosmology, in the sense that we arrived at the standard models in both cases. We don't have any definite signal beyond the standard model, and that's interesting. We'll see. I hope there will be, but who knows? Okay, thank you.
Thank you very much for this very exciting review of standard cosmological model. Questions?
So I would say that the main differences between the two standard models is that the standard cosmological models includes dark matter, while the standard particle model does not.
I agree, yes. I agree completely that there are signals coming from cosmology that tell that the standard model is not the whole story. I do hope we will detect dark matter either at accelerator, at colliders, or underground, underwater. But again, nothing is guaranteed in cosmos.
Other?
What is the so-called axis of evil axis?
There are several anomalies in WMAP data. And before Planck releases its data, it's very hard to tell which anomaly is the property of cosmic microwave background and which anomaly is the property of experiment, the systematics in experiment. The axis of evil is one of these anomalies that quadrupole and octupole they are oriented in a pretty special way. They are aligned together. Okay? Their axes are aligned, quadrupole, octupole. So low multipoles have this funny property. Another feature, which may or may not be there, again at large multipoles or large angular scales, you have even visible, anomalies like cold spots here and especially here. These are big regions with lower temperatures, and as such, if you do analysis in terms of, for example, wavelets, the abnormal features of these cold spots seem to be statistically significant. There is a lot of debate about it as well. So there are numerous, especially at low multipoles, there are numerous features that may or may not be property of cosmic microwave background. So it will be very interesting to look at the Planck data also from this respect, because some of low L features may come from systematics, because it's a very complicated procedure to actually get this map out of raw data. You have to clean, you have to do a lot of sophisticated analysis. So that's another expectation for Planck, that it will clean up the anomalies of W.
Other questions? If not, let's thank once again. And let me remind you that the results of the Young Scientist competition will be announced after the second lecture today, and diploma will be delivered, so be present at this ceremony, please, to congratulate your colleagues with us. Coffee break.